So, welcome to lecture number 13 of our course on fundamentals of transport processes. In the last 12 lectures, we had derived the equations of motion for fluid flow, and now it is time to start solving them. So, before we go to solutions, let us just briefly review everything that we have done so far. So, the mass conservation equation . The mass conservation equation can be written in the Eulerian reference frame, in a fixed reference frame at each point in the fluid as partial rho by partial t plus the divergence of rho u is equal to 0. This just reflects the fact that in a moving material reference frame, in which all points are moving with the same velocity as the fluid velocity at that point, there should be no net change of mass within a differential volume. Alternatively, in terms of the substantial derivative, this can be written as d rho by dt plus rho partial by partial xi of the velocity is equal to 0. D rho by dt plus rho times divergence of the velocity field is equal to 0, and if the fluid is incompressible, the equation just reduces to partial ui by partial xi, which is equal to the divergence of the velocity is equal to 0. Important to keep in mind when I write it in this fashion, this is valid only in a Cartesian coordinate system. The divergence operator has different forms in different coordinate systems, because in the spherical and cylindrical coordinate systems, for example, the coordinate the unit vectors depend upon position, and so you got to take the derivatives of the unit vectors with position as well. Okay. So, this is the incompressible mass conservation equation. Divergence of velocity is equal to 0. That means that the radial part, the isotropic part of the rate of deformation tensor is 0. Locally in every volume, there is no volumetric expansion or compression. Next, the momentum conservation equation can be written in a couple of different forms: partial of rho ui by partial t plus d by dxj of rho ui uj is equal to minus is equal to partial T I j by partial x j plus rho A I, okay, where T I j is the stress tensor, second order tensor, T I j is the force per unit area acting in the I direction at a surface whose unit normal is in the j direction, okay, at each point in the fluid. So, there are 9 components of the stress tensor which are defined at each and every point within the fluid. From the angular momentum conservation equation, we know that T I j is a symmetric tensor. Okay. So, T I j is equal to T j I. Okay. And as with our derivation in the case of the rate of deformation tensor, where we separated it out into a symmetric, antisymmetric and an isotropic part. So, there was an isotropic part which was basically something times an identity tensor. Then there was a symmetric traceless part, a symmetric tensor which had the property that the sum of the diagonal elements was equal to 0 plus an antisymmetric part. So, in this case the tensor is symmetric. So, I can only separate it out into 2 parts. One is an isotropic part proportional to the identity tensor, and the second is the symmetric traceless part. Okay. So, this for a static fluid, the isotropic part is just basically the negative of the pressure, because the isotropic part is basically the force per unit area acting along the outward unit normal for a differential volume. The isotropic part is the force per unit area acting along the outward unit normal for each and every volume. the pressure as we classically define it acts along the inward unit normal. Therefore, it's the isotropic part in the absence of flow is just minus p times delta ij. Then there is a second part which is non-zero only when there is flow, okay, tau ij. Okay. If this tensor is symmetric traceless, in other words, if the flow does not add to the isotropic part, then this symmetric traceless tensor, okay, was postulated to be a linear function of the velocity gradient. Okay. Now, if it is a linear function of the velocity gradient, you know that the velocity gradient, the rate of deformation tensor, can be separated out into symmetric traceless, isotropic and antisymmetric. This tau ij is symmetric traceless, it is only a function of the velocity gradient and it is linear. It has to be a linear function of the velocity gradient, not a quadratic function. It cannot be just proportional to the velocity itself, because if I move the entire equipment with a constant speed, there should be no internal stresses that are generated. It cannot be proportional to the antisymmetric part of the rate of deformation tensor, because at a given location, the antisymmetric part represents the solid body rotation around that point. And when a solid body revolves, the distances between points, material points in that body do not change. So, there is no deformation. So, it cannot be a function of the symmetric antisymmetric part. Okay. The only thing it can be a function is the symmetric traceless part. Okay. And this, if it is a linear relationship, then the only relation that you can have is a constant times the symmetric traceless tensor. I should be consistent and use the notation Eij, okay, symmetric traceless tensor, and the constant coefficient sitting in front is 2 times the viscosity. Okay, is 2 times the viscosity. Okay. So, that is the symmetric traceless part of the rate of deformation tensor. Okay. It is possible that due to flow, if you fluid was compressible, in general you could also have an isotropic part due to the rate of deformation tensor, and an isotropic part due to the rate of deformation tensor has to of course be proportional to the divergence of the velocity itself. So, in general you could also have another contribution which went as a coefficient times partial ui by by partial x k. Okay. You could have another contribution if the fluid was compressible, because as you can see, this is the divergence of the velocity. However, since we are restricting our discussion to incompressible fluids, this contribution is 0, and all you are left with is 2 mu times Eij, where Eij, as you recall, was a symmetric traceless part of the rate of deformation tensor, which was half that is the matrix plus its complex conjugate minus the trace. Okay. And since the divergence of the velocity is 0, this term is also equal to 0. Okay. So, those were our Navier Stokes mass and momentum conservation equations. Okay. To write it out in detail once again, the mass conservation equation is just that partial ui by partial xi is equal to 0, or divergence of the velocity is equal to 0. Okay. The momentum conservation equation, I can write it in 2 ways: partial of rho ui by partial t plus partial by partial xj of rho ui uj is equal to partial by partial xi of minus p, and I should take j here, delta ij plus 2 mu Eij plus rho Ei. And this thing can be simplified a little bit. Okay. As you know, if I subtract out ui times the mass conservation equation from this, right, I can expand out the left hand side to get rho partial ui by partial t plus rho uj partial ui by partial xj plus ui into partial rho by partial t plus partial by partial xj of rho uj. Okay. I just use the chain rule for differentiation for the left hand side. This entire term is identically equal to 0 because that is the mass conservation equation. Okay. On the right hand side, I have minus partial by partial xj of p times delta ij. Okay, partial by partial xj of p times delta ij, non-zero only when I is equal to j. So, this is just equal to minus partial p by partial xi, okay, plus coefficient of viscosity. If that is a constant, you can take it out, 2 mu partial by partial xj of half partial ui by partial xj plus partial uj by partial xi plus rho ei. Okay. These two half and 2 will cancel out, okay, and I can write this as minus partial p by partial xi plus mu partial by partial xj of partial ui by partial xj plus partial uj by partial xi plus rho ei. Okay. In this second term here, xi and xj are independent coordinates. So, you can interchange the order of differentiation. Partial by partial xj of partial uj by partial xi is also partial by partial xi of partial uj by partial xj, and partial uj by partial xj is just the divergence of the velocity, which as we know is 0. Okay, the divergence of the velocity is equal to 0. So, therefore, my final equation becomes minus partial p by partial xi plus mu d square by dxj square of ui. Okay. D square by dxj square is just the Laplacian del square, okay, of this vector. Okay. So, my final Navier-Stokes mass and momentum equations for an incompressible fluid. The divergence of the velocity is equal to 0, partial ui by partial xi is equal to 0, repeated index, dot product, scalar, okay, and rho into partial ui by partial t plus uj partial ui by partial xj is equal to minus partial p by partial xi plus mu partial square ui by partial xj square. Okay. Rho into partial u vector by partial t plus u dot grad. Note that the index j is repeated. So, u dot grad u vector is equal to minus gradient of p plus mu del square u vector. Vector equation, 3 components of the velocity. So, there are 3 equations here plus 1 mass conservation scalar equation, 4 unknowns, the 3 components of the velocity, 1 pressure, and so you can solve for all of them. Okay. And finally, I discussed boundary conditions at the end of the last class. Okay. This is a second order differential equation in the spatial coordinates, first order in time. Since it is second order in the spatial coordinates, you need 2 boundary conditions for each coordinate. Okay. The boundary conditions are basically at an interface between, let us say, 2 fluids. Okay. Let us say I have fluid 1 with density rho 1 mu 1, viscosity mu 1, and rho 2 mu 2. At the interface itself, you require that there should be continuity of velocity and stress. Okay. That means continuity of velocity means at the interface, the velocity in fluid 1 has to be equal to the velocity in fluid 2. That is, all three components of the velocity in fluid 1 have to be equal to all three components, the appropriate components of the velocity in fluid 2. Okay. And then there also has to be a force balance. That is, the normal forces on both sides have to be equal and the tangential forces on both sides have to be equal. Okay. So, that is what is meant by continuity of velocity and stress. These are general, they hold for any fluid. Okay. The continuity of velocity basically means that if I have an interface, right, the velocity in fluid 1, okay, and the velocity in fluid 2 at that interface, okay, the velocity in fluid 2 at a given point on the interface, the velocity in fluid 1 and the velocity in fluid 2 have to be exactly the same, which means that the normal components of the velocities have to be the same and the tangential components of the velocities in the two fluids have to be exactly the same. Okay. So, now you can define the unit normal to the surface as n. Okay. N is in general the unit normal to the surface going from one fluid to the other. Okay. So, if the velocities are equal, that means that the normal components are equal. That means that u1 I n I is equal to u2 I n I. Okay. Or alternatively in vector notation, u1 dot n is equal to u2 dot n. That is the normal component, the component of the velocity at the interface along the direction of the normal in fluid 1 has to be equal to that in fluid 2. Otherwise, you will have a velocity discontinuity at that point. Fluid 1 is moving faster or slower than fluid 2 at that point, and the velocity is double valued. Velocity is a single valued function of position. Therefore, you cannot have two values of the velocity at a given location, even if that location is an interface. Okay. That is one thing. The second is that the tangential components also have to be equal. How do we write down the tangential components? Tangential component is perpendicular to the normal. Okay. It is in the plane perpendicular to the normal. It can be in any direction in that plane perpendicular to the normal. Okay. The way you get the tangential component of a vector is to take delta ij minus ni nj times uj1. Okay. So, delta ij minus ni nj, where n is the components of the unit vector perpendicular to the surface, the unit normal. So, it has three components along the three directions. So, I goes from 1 to 3. The resultant is a vector. Okay. So, delta ij minus ni nj times any vector is a resultant is a vector. Okay. It is called the tangential component of the original vector. Okay. It is called this because if I take the dot product of this with the unit normal, okay, if I take the dot product of this with the unit normal, I will end up getting 0. Let us see how that happens. So, this is a vector. Okay. So, this is a vector, j is repeated. So, it is a dot product. The free index is I. Okay. The free index is I. So, therefore, if I want to dot this with the unit normal, I have to multiply it by n I. Okay. If I multiply it by n I, what I get is n I into delta I j minus n I n j times A j. Okay. N I times delta I j is n j because it is non-zero only when I is equal to j. Okay. N I times n I n j is n I square n j. Okay. This whole thing times n j. What is Ni square? Ni square, as you know, when you have a index repeated 2 times, that means there is a summation. So, Ni square is n1 square plus n2 square plus n3 square. The sum of the 3 components of the squares, the sum of the squares of the 3 components of that unit vector. The vector is a unit vector. That means that the sum of the squares of the 3 components has to be equal to 1. So, Ni square is equal to 1. Therefore, I have Nj minus Ni square Nj. So, this whole thing just reduces to 0. Unit normal times this vector is equal to 0. That means that this vector is perpendicular to the unit normal. Okay. This vector is perpendicular to the unit normal. Okay. And so, this is the tangential component. Okay. The normal component is just given by is equal to Ni Ai. Okay. That is the I am sorry, I should put as Nj Aj. Okay. Now, what do you get when you subtract out this from the original unit vector? When I subtract out this one from the original unit vector, I will get Ai minus delta Ij minus Ni Nj Aj. Okay. So, I have my original unit vector. Okay. I have original vector A. This is a unit normal. Okay. And I told you that this one, okay, delta Ij minus Ni Nj Aj is tangential unit vector. If I take A minus this tangential vector, I should get a vector that is along the unit normal. Okay, because you subtract out these two, you should end up with a vector which is along that unit normal. Okay. And that vector you can write Ai as Aj delta Ij Ai can always be written as Aj times delta Ij, because delta Ij is 1 only when I is equal to j, minus delta Ij minus Ni Nj into Aj. You can subtract out these two quite easily to just get simply Ni Nj Aj, which is equal to the magnitude of A along n. Okay, this is just equal to n vector, Ni free index, that means that represents the vector direction, times A dot n. So, this is the vector along the unit normal whose magnitude is equal to A dot n, the normal component. Okay. So, the sum of these two basically will end up giving you the total vector, the component along the normal plus this tangential component, which is delta Ij minus Ni Nj times Aj. Okay. So, this thing is called the transverse projection operator. It gives you the component of the vector which is perpendicular to the direction n. That is the tangential component of the velocity. That has to be equal on both sides. Okay. That has to be equal on both sides. So, this is equal to delta Ij minus Ni Nj times the vector in the second fluid. Okay. Or this is also often written as the identity tensor minus n n dotted with u is equal to minus n n dotted with u, the second fluid. Okay. So, that is how you would write the boundary conditions for the tangential component of the velocity. The other boundary condition that you need is the continuity of stress at the surface, that is the force per unit area, both normal and tangential to the surface, have to be equal on both sides. The tangential stresses have to be equal, because you cannot have a net force that is exerted by the interface itself. Okay. But however, you can have a net force normal to the surface exerted by the interface, that is the force of surface tension. Okay. So, the surface tension force acts normal to the surface. Okay. Now, for the tangential component of the stress, the force acting at that surface and with unit normal n. Okay. So, at this surface that I have with unit normal n, the force per unit area that is acting is the stress tensor dotted with n. Okay. The force per unit area that is acting is a stress tensor dotted with n. Okay. So, the force per unit area in fluid 1 is equal to T I j 1 times n j, And we said that the tangential component of the force per unit area in fluid 1 has to be exactly the same as the tangential component of the force per unit area in fluid 2. Okay. Okay, Tij1 and j. Okay. The tangential component of this I get by just multiplying it by the transverse projection operator. Okay. So, I have I should have some other symbol here when I use the transverse projection operator. So, I will write this as T j k 1 and k into the transverse projection operator, which is delta I j minus n I n j. Okay. That in fluid 1, that is the stress that is along the tangential direction on both sides of the interface. Okay. The force along the tangential direction on both sides of the interface have to be equal. This is equal to delta I j minus n I n j into T j k 2 n k. Okay. So, that is the tangential stress balance condition. On both sides of the interface, the tangential forces have to be equal. For the tangential component of the stress, there is no contribution due to the pressure, because pressure always acts perpendicular to the surface. Okay. So, there is no contribution to the pressure due to the tangential component of the stress. Okay. So, therefore, the tangential component alone, I can write this as delta I j minus n I n j into the shear stress tau j k 1 and k is equal to delta I j minus n I n j into tau j k 2 and k. Okay. So, the two components of the shear stress tangential to the surface have to be equal on both sides. Okay. Finally, for the normal component, okay, the force acting at the interface itself is equal to T j k 1 and k. Okay. The normal component of this is this dotted with the unit normal. Okay. The normal component of force acting at the interface is just this dotted by the unit normal. Okay. That is this dotted with n j. Okay. This on the other side, it is n j T j k 2 n k. However, the two need not be equal, because the interface itself can exert a surface tension, force per unit area, due to the curvature of the surface. That surface tension force also has to be incorporated here. Okay. This surface tension force is in general written as the coefficient of surface tension times 1 by R 1 plus 1 by R 2, where R 1 and R 2 are the principal radii of curvature along the surface, the maximum and the minimum. These two, maximum and minimum, are always along orthogonal directions on the surface. Okay. So, if I have a surface that looks something like this, okay, a curved surface, I will have two directions along which the radii of curvature are either maximum or minimum, and these are two perpendicular directions, and along those two directions, if you calculate what is 1 by R 1 plus 1 by R 2, that times the surface tension coefficient gives me the difference in the stress along the between the two fluids. Okay. This difference in stress can also in general be written in terms of the divergence of the unit normal. Okay. The unit normal is given by n, and the divergence along the surface gives you. Okay. So, if I have a unit normal n is equal to unit normal n that is perpendicular to the surface. Okay. I can take the surface divergence del s of n, okay, which is equal to the divergence of the unit normal along two orthogonal directions along the surface itself. Okay. And that divergence of n can also be used instead of 1 by R 1 plus 1 by R 2. Okay. That is a little bit outside the scope of this course. So, I will not discuss that in detail, but just to show you that basically this surface tension force can also be expressed in terms of the divergence of the unit normal at the surface. Okay. However, it is strictly speaking proportional to 1 by r 1 plus 1 by r 2, where r 1 and r 2 are the two principal curvatures. Okay. So, this is for the interface between two fluids in general, right. If you have an interface between a fluid and a solid, the solid is assumed to be rigid. That means that no matter how much the force is exerted on that solid, it does not deform, it is a solid object. Okay. It is not like a fluid which deforms continuously upon application of stress. Okay. The solid will deform to some extent and then stop. Okay. So, in a steady state, the solid will have some deformation, but it will not continuously deform under flow. In those cases, what the boundary condition that is used is that the velocity of the fluid at the surface is equal to the velocity of the surface solid itself. Okay. So, for a solid fluid, all you enforce is that the velocity of the solid is equal to the velocity of the fluid at the surface of the solid is equal to the velocity of the solid itself. Okay. That means that the velocity of the fluid at the solid interface. So, if I have some solid object here which is moving with some velocity u, we call that as capital U. Capital U is the velocity of the solid. That means each point on the surface of that solid is moving with exactly that same velocity, because it is a rigid object. Okay. On the other hand, if it is rotating, in general you will have a translational velocity plus a rotational velocity, okay, of the solid around its axis of rotation. Okay. In any case, for the solid fluid interface, the boundary condition that you impose is that the velocity of the fluid at the surface is equal to the velocity of the solid itself, if it is just purely translating. Okay. If it is rotating as well, okay, then the velocity on the surface is equal to omega cross r, where r is the distance, okay, from the center of rotation to that point on the surface. Okay. So, in that case you define this as r cross omega, where omega is the angular velocity, okay, and r is the distance from the center of rotation to that point on the surface. Basically, the velocity of the fluid at the surface is equal to the velocity with which the solid surface is moving at that point. Once you do that, there is now no necessity to impose the stress boundary conditions, because the solid will generate whatever stress internally is required to balance the fluid stress at the interface. Okay. So, that is the basic idea of the no slip condition at a fluid solid interface. It is always valid unless for some reason the length scale of the flow becomes comparable to the mean free path. Okay. Now, for a gas liquid interface, okay, the viscosity of a gas is typically much smaller than the viscosity of the liquid. Typically, the gas will have a viscosity that is between 1/100th to 1/1000th the viscosity of a typical liquid. Okay. So, in that case, what one can do is to say that the shear stress which is generated by the viscosity of the gas is negligible compared to the viscosity of the liquid. So, what you do is to set the tangential stress at in the liquid equal to 0 at the liquid gas interface. So, for the shear stress, you would impose the condition that delta I j minus n I n j times tau j k n k is equal to 0 for the liquid, because the gas has a negligible viscosity. So, it is exerting a negligible shear stress. Therefore, the shear stress in the liquid has to come down to that same value as you approach the interface. Okay. And the normal stress boundary condition is exactly the same as this one. Okay. The normal stress boundary condition that you would apply at a gas liquid interface is exactly the same as this one. Okay. So, this is n j t j k 1 n k minus n j t j k 2 n k is equal to gamma into 1 by r 1 plus 1 by R 2. Since the viscosity of the gas is negligible, the main contribution to the normal stress in the gas is going to be only due to the pressure. Okay. So, that the pressure term just becomes N j into minus P delta J k, okay, times N k, where P is the pressure in the gas. Okay. And this, as you can see, N j delta J k times N k is just N j square, which is 1. Okay. So, this just reduces to N j square, which is 1, because it is isotropic. Okay. Therefore, I just get minus the pressure in the gas. Okay. N k minus of this is equal to gamma into 1 by R 1 plus 1 by R 2. Contrast to the liquid solid interface, in this case we do not worry about the velocity boundary conditions. The velocity at the gas liquid interface is allowed to slip. The velocity need not approach 0 as you approach the interface. What is required is that the shear stress has to be 0, because the viscosity of the gas is negligible. The normal stress difference, you neglect the viscous terms in the normal stress for the gas, and you have only the pressure term. Okay. In the liquid, of course, you will have both the viscous and the pressure terms. Okay. So, that completes the specification of the governing equations and the boundary conditions, okay, for the flow. As I said, the next step is to try to solve these equations. Before proceeding to the solution, I just like to spend some time in deriving the energy balance equation for fluid flow. The energy balance equation does not contain any additional information. Okay. It's just obtained by dotting the momentum conservation equation with the velocity itself. However, it does contain an important piece of information, which is about the viscous dissipation, okay, the conversion, the fluid friction which converts the mechanical energy into heat energy inevitably in any process. Okay. So, let us go back and look at the momentum conservation equation. Okay. Momentum conservation, this equation is rho times partial u I by partial t plus u j is equal to minus partial p by partial x I plus partial by partial x j of tau I j, the shear stress, plus rho times A I. I get the energy balance equation by multiplying this by u I, okay, dotting the entire momentum conservation equation with the velocity itself to get the mechanical energy balance equation. Okay. So, this energy balance equation, I just multiply this whole thing by the velocity itself, u I. And you can see, for example, u I times partial u I by partial t is just equal to rho times partial by partial t of half u I square. Okay. U I times partial u I by partial t is equal to partial by partial t of half u I square. Similarly, rho u j times partial u I by partial t, when you multiply it by u I once again, you just get u j partial by partial x j of half u I square minus u I partial p by partial x I plus u I partial by partial x j of tau I j plus rho A I u I. That is the mechanical energy conservation equation. I can sort of convert this into a more transparent form by just adding half u I square times the mass conservation equation. Okay. So, if I take half u I square times partial rho by partial t plus partial by partial x j of rho u j equal to 0. Okay. Mass conservation equation itself is 0. So, if I multiply it by half u square, I will still get 0. Add up these two, and what you get is partial by partial t of half rho u I square plus partial by partial x j of half rho u I square u j. Okay. The terms on the right, I use integration by parts to simplify them. Okay. So, I get minus partial by partial x I of p times u I, okay, plus p partial u I by partial x I, okay, one integration by parts. second integration by parts for the shear stress. So, plus partial by partial x j of rho tau I j u I minus tau I j partial u I by partial x j plus rho e I u I. Okay. Just use two integrations by parts, okay, for these two terms. Okay. Half rho u I square is the mechanical energy per unit volume. Half m u square is the kinetic energy, and that divided by volume. Rho is a mass per unit volume. So, half rho u I square is the fluid kinetic energy per unit volume. Okay. So, therefore, on the left hand side I have partial by partial T of the kinetic energy per unit volume plus partial by partial x j of u j times the kinetic energy. Okay. Note that E kinetic is a scalar, okay, it is the kinetic energy per unit volume. Okay. Is equal to minus partial by partial x I of P u I plus partial by partial x j of tau I j u I. Okay. So, those are the first two terms, those are these two terms, okay, and then I have these two terms, okay, which came out of the integration by parts. Okay. So, those will be plus P partial u I by partial x I, okay, minus tau I j partial u I by partial x j plus rho a I u I. Let us look at the physical interpretation of all of these terms. Okay. On the left hand side I have partial by partial T of the kinetic energy plus partial by partial x j of u times the kinetic energy. By Leibniz rule, that is the kinetic energy change in a moving differential volume of fluid. Okay. By Leibniz rule, this is the kinetic energy change in a moving volume of fluid. Okay. These two terms here, they are both divergence of something integrated over, and if you calculate these two terms for a differential volume, these are the divergence of something integrated over that volume, which is the same as n dot that thing integrated over the surface area. So, these contribute a surface flux. The first term here is a surface flux of energy due to the pressure work done at the surface. The first term is the surface contribution to the energy, divergence of P u I, which is basically the pressure work done at the surface. The integral of that times the unit normal will basically give you this. This second term here is the surface work done by the shear stresses. Okay. The divergence of tau dot n integrated over the volume is equal to, I am sorry, the divergence of tau dot u integrated over the volume is equal to n dot tau dot u integrated over the surface. The other two terms at the bottom, of course, the last term is just the work done by the body force, the acceleration due to the body force. So, that is rho a I times u I, but the other two terms here are actually volumetric terms. Okay. The first term is actually P times partial u I by partial x I, P times divergence of u. Okay. For the general compressible fluid, the mass conservation equation that we had was that d rho by dt plus rho del dot u is equal to 0. Okay. That means that the del dot u is equal to minus 1 by rho d rho by dt. Okay. So, therefore, using that, this term can also be written as minus p by rho d rho by dt. Okay. The work done due to volumetric expansion or compression due to the change in density of the fluid. Okay. So, that is this term here. This is reversible in the sense that if the density increases, the work will be there will be work done when the density decreases, when the volume increases, the fluid does work on the outside, whereas when the volume decreases or the density increases, work is done on the fluid. So, this is a reversible work term. Okay. This final term is called an irreversible work, okay. And this is the cause for heating within a fluid to viscous friction. You can show that this term always has to be positive, okay. You can show in general that this term always has to be positive, okay. That is, the viscous dissipation of energy is equal to tau ij partial ui by partial xj. This is the dissipation rate, dissipation of energy per unit volume, okay. And in this equation here, this appears with a negative sign, okay. This appears with a negative sign here. So, therefore, it is always removing energy from the fluid, it is always decreasing the kinetic energy of the fluid. So, if I expand out this term, you will see that this is equal to 2 mu Eij times partial ui by partial xj, okay. Eij is a symmetric traceless tensor, okay. Eij is a symmetric traceless tensor, okay. Therefore, when I multiply Eij times partial ui by partial xj, okay, this partial ui by partial xj is given by the sum of the symmetric plus the antisymmetric part, okay. The rate of deformation tensor can be separated into symmetric plus antisymmetric part. The product of Eij, which is symmetric, and Eij, which is antisymmetric, is 0, okay. Therefore, this can also be written as 2 mu Eij times Sij, okay. And you know that Eij is the symmetric traceless part, Sij is the symmetric part, Eij is the symmetric traceless part, okay. So, this is just equal to 2 mu, the symmetric traceless part is just Sij minus 1/3 delta ij times the trace, okay, times the trace times Sij, okay. For an incompressible fluid, Skk is equal to 0, this is the divergence of the velocity, this is identically equal to 0, okay. Therefore, this is identically equal to 0, and you can see that d is equal to 2 mu times the product of two symmetric tensors, okay. The product of these two symmetric tensors will always be positive, okay, because both tensors are symmetric. Therefore, whether the off diagonal terms are positive or negative, the product of those two will always end up being positive, okay. Basically, it is equal to S11 square plus S22 square plus S33 square plus 2 times S12 S21 plus S13 S31 plus S23 S32. So, it will always be positive. So, this is always greater than or equal to 0. In fact, the result is more general than that. You can show that even for a compressible fluid, if you retain this isotropic part, you can still show that d is always positive, okay. I will not go through that here, it involves a little bit of algebra, but it is quite simple to show that even if you have a compressible fluid, d is always positive. So, therefore, this represents the irreversible dissipation of energy, the conversion of mechanical energy into heat, and that is appearing, as you can see here in this equation. That conversion is appearing as a sink term in the energy conservation equation. It always tends to reduce the energy of the fluid, okay, and therefore, it always dissipates energy, converts mechanical energy into heat, and that is what causes losses in fluid flow. The pressure gradient, for example, which you apply between the ends of the pipe in order to force fluid through it, is because the energy is being constantly dissipated within the fluid into heat energy due to this dissipation term. Happens only for a viscous fluid, okay. If the viscosity were 0, then I just have the Euler the pressure term, which was reversible. But however, all fluids have a non-zero viscosity, therefore, they always convert energy from mechanical energy to heat energy, and that causes dissipation in fluid flows. Okay. So, that is the energy balance equation. As I said, it is only for the mechanical energy balance equation, okay. So, whenever if you want to estimate how much heat is generated due to the fluid flow, the dissipation rate, okay, in the fluid is basically going to be equal to tau ij times partial ui by partial xj, okay. So, this completes our derivation of the conservation equations, the constitutive relations, the boundary conditions, and I talked briefly about energy dissipation. Okay. So, that completes our derivation. Next step is to go ahead and solve those equations. Okay. Let us write down our Navier-Stokes equations again. Okay. Divergence of velocity is equal to 0. Okay. Rho times partial ui by partial t plus mu times partial square ui j square plus rho times acceleration. Note that acceleration is the equivalent of the source or sink terms that we had in the mass and momentum conservation equations. This is the equivalent of the diffusion terms, the viscous term. These are the inertial terms, the convective terms. We have the pressure here, which is not present in normal heat and mass transfer, and we also have the condition that the divergence of the velocity has to be equal to 0. There is no radial component of the velocity field. And now we will try to solve these equations in different limits. If you recall, when we did heat and mass transfer, we solved it in the limits of where diffusion dominates and where convection dominates. Similarly, in this case also we will solve it in the cases where diffusion dominates and convection dominates. Okay. But before that, we will just think back and derive some simple results that we got for unidirectional flows in the course on fundamentals of transport processes 1, okay, just based upon shell balances. These equations are more general, but we have to be able to show that these also reduce to those same equations, okay, that we obtained using shell balances. Okay. So, we look at some simple unidirectional transport problems first before we go on to looking at more complicated ways of solving these equations. After all, we derived these equations in order to express everything in terms of vectors without reference to the underlying coordinate system. Okay. Whereas, when we did shell balances, we always had a coordinate system, wrote down a shell that was appropriate for that, and then solved it. Okay. So, when we go on to our next solution of low and higher Reynolds solutions of these equations, we will look at it independent of coordinate systems. But first, look back at the solutions that we had derived using shell balances and check that we obtain the same solutions here as well. The simplest case that one can consider is when the velocity is completely 0. Okay. In that case, the equivalent mass and heat transfer cases, the temperature or the concentration are uniform everywhere. There is no problem to solve. Okay. In this case, however, because we have a pressure, there is a problem to solve. Okay. Hydrostatics. Okay. Velocity is 0 everywhere. Okay. Mass conservation equation is trivially satisfied. In the momentum conservation equation, I have minus partial p by partial xi plus rho times ai is equal to 0, or the gradient is equal to rho times ai. The gradient of the pressure is equal to rho times the acceleration. This I can integrate quite easily if density and acceleration are independent of position. If rho and ai are constants, then the equation is quite easy to integrate. Okay. The solution is just that p is equal to rho aj times xj, okay, because the density and the acceleration are both constants. So, with this solution, I can verify that I get the correct result. Okay. Partial b by partial xi is equal to partial by partial xi of rho aj xj. Okay. So, rho and a are independent of coordinate. Therefore, I have partial by partial xi of aj. Partial xj by partial xi is 1 if j is equal to I, that is partial x1 by partial x1 is 1. It is 0 if j is not equal to I. So, this just becomes equal to rho aj times delta ij. And you can verify that this is exactly equal to the right hand side that is required. Okay. So, it is equal to rho A j x j, but however, when I take gradients I can always put in a constant. Okay. So, some constant plus this, because when I take the gradient of the constant it becomes 0 anyway. So, that is the solution for hydrostatics, P is equal to P naught plus rho A j x j. Okay. The simplest case, if I had for example, a fluid in a gravitational field and the acceleration due to gravity was acting conventionally in the minus z direction, if the acceleration due to gravity was acting conventionally in the minus z direction, I will just get equal to P naught minus rho g z. Okay. The familiar expression in hydrostatics, okay. The pressure at a point is equal to P constant minus rho g z, where that constant depends upon where you fix your reference location, the location at which z is equal to 0. So, this is the fundamentals of hydrostatics. Okay. All hydrostatic problems can be reduced to exactly this. Okay. The next simplest case one can consider, which we considered earlier as well in fundamentals of transport processes 1, is a unidirectional flow. In a unidirectional flow, the velocity is only along one direction. The velocity variation in general is only along the second direction. Okay. So, if you have a simple flow in a fluid, in a pipe or in a channel, okay. In this particular case, if I had a channel flow in which I use my coordinates x and y, the velocity will be along the x direction, the velocity gradient will be along the y direction. Okay. And of course, in general, okay, this is a two-dimensional problem, and I will have to expand out my Navier-Stokes equations for this two-dimensional problem, and many terms will simply drop out simply because the velocity gradient is only along one direction, the velocity is only along one direction. So, we will look at that in the next lecture, see how the Navier-Stokes equations can be easily applied to solve one-dimensional problems. Of course, it is a simplification. We take the original equations, simplify them under these assumptions, and then solve the simplified equations. However, the simplified equations that we get should be identical to what we got using shell balances, and the solutions should be identical as well. So, we will continue that in the next lecture before we go on to more complicated solutions. Okay. For example, solutions where there are velocities in all three directions. Okay. That we will consider in two limits. One is in the viscous, the diffusion dominated limit, and the other is in the convection dominated limit. So, we will start off with simple unidirectional flows in the next lecture before looking at more complicated flows. So, we will see you then, and we will continue the next lecture.